Spectroscopy and spectrometry, sources, detection, and data acquisition. Both spectroscopy and spectrometry utilize the interaction with light with matter. In spectroscopy, photons of light are absorbed. Transition energies equal photon energies with the Planck relationship delta E equals h times frequency, defining the energy relationship with the transition. In spectrometry, light frequencies match transition frequencies. Resonance occurs between light waves and matter waves. Resonance is also related to frequency. Therefore, both types of techniques are dependent upon the frequency of radiation. And since all radiation travels at the speed of light, which is equal to wavelength times frequency, wavelength equals frequency over the speed of light, and both techniques are wavelength dependent. All techniques use what is called broadband sources, where white radiation is emitted across a continuous band of wavelengths. For the various techniques in UV visible radiation, deuterium lamps provide light or radiation within 160 to 400 nanometers and are generally used as the ultraviolet source between 190 and 340 nanometers. Tungsten filament lamps emit between 300 and 2500 nanometers, but are restricted as the visible source between 300 and 700 nanometers. In Raman spectroscopy, as you saw, lasers are used as a constant wavelength light source. Therefore, the wavelength range is tied to the laser because Raman measures the shift in wavelength as the light interacts with the vibrational waves of the bond. For infrared spectroscopy, silicon carbide glow bars are generally used, which have emissions between 4,000 and 15,000 nanometers, and therefore can be used in the far, mid, and near infrared ranges. For microwaves, a tuned cavity emitter is used. These emitters can be used between 1 millimeter and 30 centimeters and are similar to the types of emitters used in a microwave oven. As a tunable source, the wavelength is related to the radius of a fixed waveguide. The same is true for nuclear magnetic resonance. A tuned oscillator is used that emits in the radio frequency of 1 millimeter to 300 kilometers. This is also a tunable source. As you may note, many sources overlap. The source of choice has the highest emission in the region of interest. Just as the emissions are broadband, all techniques use broadband detectors. Detectors with sensitivity over a broad range of wavelength. For the UV visible spectroscopy, the ultraviolet range between 190 and 325 nanometers, and the visible range between 325 and 700 nanometers, we'll use either a Photodiode Array or a Photomultiplier Tube as the detector. For Raman spectrometry, again, the wavelength range is any range depending on the laser used, because you are looking for a shift, and photodiode arrays are used as a detector. Similarly, for infrared, in the mid to far range, between 4,000 and 15,000 nanometers, so that's the mid to near range, a photo array diode is also used. For microwaves, between 1 millimeter and 30 centimeters, a tunable detector is used. Similarly, for an NMR, between 1 millimeter and 300 kilometers in the radio range, a tunable detector is also used, where the detector can be tuned in to the range of the resonance. As you have just seen, multiple types of detectors can be used. The most common is a photodiode array detector. In electronics, a diode, whose schematic is shown here, is a current rectifier. Ideally, a diode has zero resistance in one direction and infinite resistance in the other direction. A photodiode, whose schematic is also shown, is a photovoltaic rectifier. In this case, photons excite an electron. Since it is a diode, a unidirectional current is produced. The magnitude of the current produced is proportional to the number of photons impacting upon the photodiode. A photodiode array is an array of p-n junction semiconductors of different composition. Different materials are sensitive in different ranges. As can be seen, silicon semiconductors are sensitive to light between 190 and 1100 nanometers. Germanium diode semiconductors are sensitive between 400 and 1700 nanometers. Indium gallium arsenide solid solutions are sensitive between 800 and 2600 nanometers. Lead sulfide, closer to the visible, 1000 to 3500 nanometers. And another solid solution, mercury cadmium telluride, between 400 and 14,000 nanometers. Again, it can be seen that many of these ranges overlap. Most sensors are tuned for their most sensitive range, and the overlapping ranges give increased sensitivity to the entire array. The original type of detector, and a detector that is still used, is called a Photomultiplier Tube, or a PMT. A Photomultiplier Tube is essentially a vacuum tube. It contains multiple dinodes. A dynode is a stack of cathodes. Each is at a sequentially higher voltage, and the initial cathode is photovoltaic. Dinodes amplify the signal. A photon strikes the photovoltaic cathode, emitting an electron. Higher voltages at each cathode produce secondary electrons. A cascade effect amplifies the signal. Photomultiplier tubes are extremely sensitive. On average, they have 10 to the 8th power amplification over the photon signal. Although they seem old-fashioned, the vacuum tube also ensures extremely low noise. PMTs are used in high sensitivity photon counting techniques. The two main detectors have been seen. Now, two basic acquisition modes shall be looked at. First of all, scanning acquisition. In this case, the broadband incident radiation is mechanically scanned. Radiation is introduced to the sample in progressively longer wavelengths. The rate of the scan and the step between increments determines the resolution. As stated, this is done mechanically. A grating monochromator is essentially a mirror. Fine bevel lines are etched onto the glass at progressively further distances. The grating is slowly rotated. The grating lines disperse the incident radiation. Only wavelengths at the blaze angle will be reflected to the sample. The geometry of the blaze angle is as follows. M lambda equals d sine alpha minus sine beta, where alpha is the angular difference between the incident radiation and the direction of the sample, and beta is the angular difference between the rotation of the mirror and the angle of the sample. D is the spacing between each of the incident etched lines. As the grating rotates, the wavelength blazed to the sample changes from purple through red. Slits are then introduced. These further discriminate the wavelength because the blaze M, the integer multiple of any given wavelength, is allowed, and therefore a slit is needed to eliminate these harmonics. The second predominant method for gathering data is called a Fourier Transform. A Fourier Transform is a mathematical function. It transforms any function of x into a new constituent set of frequencies, eta, where mathematically f of x is equal to the integral from infinity to minus infinity of f bar of eta e to the 2 pi I, where I is the imaginary number, x eta d eta. Conceptually, this is simple. For a spectrum, x is time, and eta is the vibration frequency. Consider the following function. It is not difficult to see that the function shown above is actually the sum of two separate wave signs that are 90 degrees out of phase. For more complicated interference patterns, as those used in white radiation, the use of a computer program to discriminate between wavelengths is convenient. Further looking at Fourier Transform acquisition, the sample is exposed to the full band radiation, meaning all wavelengths are simultaneously shown upon the sample, similar to turning on a light bulb. However, the radiation is pulsed. In this case, each pulse is a separate scan. Interference patterns are then received, spaced at constant timings. As you can see, These interference patterns, called frequency-induced decays, or FIDs, are the sum of the intensities of all frequencies of the radiation. Irregularities in the shapes are due to absorption of various frequencies by the sample. Fourier transforms are based purely on timing. The raw data, as you saw, was based on intensity versus time to be received by the receiver. The desired transform is to convert time into radiation frequency. Therefore, a clock is needed to provide the Fourier transform with a constant time interval. This is something a computer is eminently capable of providing. For FTIR, a laser interferometer is used. A helium neon laser vibrates at a known frequency. The beams produced bounce between a pair of mirrors. After a known number of passes, the vibration of the laser creates an interference pattern where there is cancellation. The wavelength of the laser, 632.8 nanometers, is known. The vibration rate of the laser is also known. Therefore, the time between interferences is calculable. A clock is now set to transform time into the FID to a specific frequency. For an FT-NMR, the situation is simpler. A quartz oscillator is used. Quartz has a known oscillating frequency. Transforming this frequency with the RF pulse duration performs the same function as an interferometer. A comparison can be made between the scanning of data versus a Fourier transform of all data gathered simultaneously. In scanning data acquisition, as mentioned, the wavelengths are mechanically scanned. Therefore, the resolution can only be increased by both shorter steps and longer scans, and also more scans. For FT data acquisition, each FID is an individual scan gathered quickly. The Fourier transform changes intensity versus time of arrival to frequency. For FTIR, 1 over lambda equals frequency divided by Planck's constant times the speed of light in centimeters. Frequency is displayed as either percent absorbance transition versus wave number after the transform. For FT-NMR, the frequency is directly related to the delta value because the frequency of resonance of the sample minus that of the reference divided by the reference equals delta. Therefore, FTIR techniques are faster because all wavelengths are scanned simultaneously. They also have generally better resolution because multiple scans can be produced in a short amount of time. It would seem that Fourier transform methods are vastly superior. So why are scanning methods still used, and when is each used? First of all, wavelength scanning is generally used in UV visible spectroscopy because electronic transitions are very strong and frequently occur. They have an inherently strong signal and therefore need only one scan. Also, as you have seen in your experiments, UV visible peaks are broad. resolution is not an issue. On the other side of the spectrum, you have fluorescence and phosphorescence. In this case, you have a narrow scanning range, so the advantage of FT for broad scanning is negated. You are only looking for differences between tenths of nanometers. Additionally, in fluorescence and phosphorescence, you are doing high precision photon counting using a photomultiplier tube. Mathematical interpretations would actually decrease sensitivity in this case. Fourier Transform is the preferred method of data acquisition in infrared spectroscopy because vibrational transitions are inherently weak and are also broad. Therefore, multiple scans are needed to increase sensitivity. And also, Fourier transforms are used predominantly in nuclear magnetic resonance, where once again, magnetic resonances are weak signals. Multiple scans are needed to resolve splitting patterns.